Alright, so we're in the Helicopter Flying Handbook. I'm in Chapter 11, Helicopter Emergencies and Hazards. This will be page 1 of 24. Ooh. Alright, introduction. Today's helicopters are quite reliable. However, emergencies do occur, whether a result of mechanical failure or pilot error, and should be anticipated. Regardless of the cause, the recovery needs to be quick and precise. By having a thorough knowledge of the helicopter and its system, a pilot is able to handle the situation more readily. Helicopter emergencies and the proper recovery procedures should be discussed and, when possible, practiced in flight. In addition, by knowing the conditions that could lead to an emergency, many potential accidents can be avoided. Auto rotation, page 2. In a helicopter, an auto-rotative descent is a power-off maneuver in which the engine is disengaged from the main rotor system and the rotor blades are driven solely by the upward flow of air through the rotor. In other words, the engine is no longer supplying power to the main rotor. The most common reason for an auto-rotation is failure of the engine or driveline, but auto-rotation may also be performed in the event of a complete tail rotor failure, since there is virtually no torque produced in an auto-rotation. In both areas, maintenance has been a contributing factor to the failure. Engine failures are also caused by fuel contamination or exhaustion, as well as resulting in forced auto-rotation. If the engine fails, the freewheeling unit automatically disengages the engine from the main rotor, allowing the main rotor to rotate freely. Essentially, the freewheeling unit disengages anytime the engine revolutions per minute is less than the rotor RPM. At that instant of engine failure, the main rotor blades are producing lift and thrust from their angle of attack and velocity. By lowering the collective pitch, which must be done immediately in case of an engine failure, lift and drag are reduced, and the helicopter begins an immediate descent, thus producing an upward flow of air through the rotor system. This upward flow of air through the rotor provides sufficient thrust to maintain rotor RPM throughout the descent. Since the tail rotor is driven by the main rotor transmission during auto-rotation, heading control is maintained with the anti-torque pedals as in normal flight. Several factors affect the rate of descent in auto-rotation: density, altitude, gross weight, rotor RPM, and airspeed. The primary way to control the rate of descent is with airspeed. Higher or lower airspeed is obtained with the cyclic pitch control, just as in normal powered flight. In theory, a pilot has a choice in the angle of descent varying from a vertical descent to maximum range, which is the minimum angle of descent. Rate of descent is high at 0 airspeed and decreases to minimum at approximately 50 to 60 knots, depending upon the particular helicopter and the factors just mentioned. As the airspeed increases beyond that which gives minimum rate of descent, the rate of descent increases again. When landing from an auto-rotation, the only energy available to arrest the descent rate and ensure a soft landing is the kinetic energy stored in the rotor blades. Tip weights can greatly increase this stored energy. A greater amount of rotor energy is required to stop a helicopter with a large rate of descent than is required to stop a helicopter that is descending more slowly. Therefore, auto-rotative descents at very low or very high airspeeds are more critical than those performed at the minimum rate of descent airspeed. Each type of helicopter has a specific airspeed and rotor RPM at which a power-off glide is most efficient. The specific airspeed is somewhat different from each type of helicopter, but certain factors affect all configurations in the same manner. In general, rotor RPM maintained in a low green area gives more distance in an auto-rotation. Higher weights may require more collective pitch to control the rotor RPM. Some helicopters need slight adjustments to minimum rotor RPM settings for winter versus summer conditions and high altitude versus sea level flights. For specific auto-rotation airspeeds and rotor RPM combinations for a particular helicopter, refer to the Federal Aviation Administration's FAA-approved Rotor Flight Manual, or the RFM. Picture time is here. Alright, so figure 11.11. During an auto-rotation, the upward flow of relative wind permits the main rotor blades to rotate at their normal speed. In effect, the blades are gliding in their rotational plane. Okay. The specific airspeed and rotor RPM for auto-rotation is established for each type of helicopter on the basis of average weather, wind conditions, and normal loading. When the helicopter is operated with heavy loads in high density altitude or gusty wind conditions, best performance is achieved from slightly increased airspeed in the descent. For auto rotation at low density altitude and light loading, best performance is achieved from a slight decrease in normal airspeed. Following this general procedure of fitting airspeed and rotor RPM to existing conditions, a pilot can achieve approximately the same glide angle in any set of circumstances and estimate the touchdown point. Pilots should practice auto rotation with varying airspeeds between the minimum rate of descent to the maximum glide angle airspeed. The decision to use the appropriate airspeed for the conditions and availability of landing area must be instinctive. The helicopter's glide ratio is much less than that of the fixed-wing aircraft and takes some getting used to. The flare to land a 55 KIAS will be significantly different from the flare for an 80 KIAS. Rotor RPM control is critical at this point to ensure adequate rotor energy for cushioning the landing. A straight-in auto rotation, page 3 of 24. A straight-in auto rotation implies an auto rotation from altitude with no turns. Winds have a great effect on auto rotation. Strong headwind causes the glide angle to be steeper due to slower ground speed. For example, if the helicopter is maintaining 60 knots indicated airspeed and the wind speed is 15 knots, then the ground speed is 45 knots. The angle of descent will be much steeper, although the rate of descent remains the same. The speed of the touchdown and the resulting ground run depend on the ground speed and amount of deceleration. The greater the degree of deceleration or flare and the longer it is held, the slower the touchdown speed and the shorter the ground run. Caution must be exercised at this point, as the tail rotor will be the closest component of the helicopter to the ground. If timing is not correct and landing attitude not set at the appropriate time, the tail rotor may contact the ground, causing a forward pitching moment of the nose and possible damage to the helicopter. A headwind is a contributing factor in accomplishing a slow touchdown from an auto-rotative descent and reduces the amount of deceleration required. The lower the speed desired at touchdown is, the more accurate the timing and speed of the flare must be, especially in helicopters with low inertia rotor systems. If too much collective pitch is applied too early during the final stages of the auto-rotation, the kinetic energy may be depleted, resulting in little or no cushioning effect available. This could result in a hard landing with corresponding damage to the helicopter. It is generally better to practice to accept more ground run than a hard landing with minimal ground speed. As proficiency increases, the amount of ground run may be reduced. Technique. Refer to Figure 11-2, Position 1 from level flight as the appropriate airspeed, cruise, or the manufacturer recommended airspeed. Alright. Straight in auto rotation. I guess, is this 11-2? Yep. All right, 500 or 700 feet above ground level, AGL, above ground level, and heading into the wind, smoothly but firmly lower the collective pitch control to the full down position, maintaining rotor RPM in the green arc with collective. All right, we need to lower the collective pitch control to the full down position, maintaining rotor RPM in the green arc with collective. If the collective is in the full down position, the rotor RPM is then being controlled by the mechanical pitch stops. During maintenance, the rotor stops must be set to allow minimum auto-rotational RPM with a light loading. This means that some collective pitch adjustment can be made if the air density or helicopter loading changes. After entering an auto-rotation, collective pitch must be adjusted to maintain the desired RPM. Coordinate the collective movement with proper anti-torque pedal for trim, and apply cyclic control to maintain proper airspeed. Once the collective is fully lowered, decrease throttle to ensure a clean split separation of the needles. This means that the rotor RPM is higher than the engine RPM and a clear indication that the freewheeling unit has allowed the engine to disconnect. After splitting the needles, readjust the throttle to keep the engine RPM above normal idling speed, but not high enough to cause rejoining of the needles. The manufacturer often recommends the proper RPM for the particular helicopter. At position 2, adjust the attitude with cyclic control to obtain manufacturer's recommended auto rotation or best gliding speed. Adjust collective pitch control as necessary to maintain rotor RPM in the green arc. As cyclic movements cause an increase in rotor RPM, which is then controlled by a small increase in collective pitch control. Avoid a large collective pitch increase, which results in a rapid decay of rotor RPM and leads to chasing the RPM. Avoid looking straight down in front of the aircraft. Continually cross-check altitude, attitude, trim, rotor RPM, and airspeed. All right. So, at altitude recommended by the manufacturer, position number 3, begin the flare with aft cyclic control to reduce forward airspeed and decrease the rate of descent. Maintain heading with anti-torque pedals during the flare. Maintain rotor RPM in the green range. Care must be taken in the execution of the flare so that the cyclic control is neither moved rearward so abruptly that it causes the helicopter to climb, nor moved so slowly that it does not arrest the descent, which may allow the helicopter to settle so rapidly that the tail rotor strikes the ground. In most helicopters, the proper flare attitude is noticeable by an apparent ground speed of a slow run. When forward motion decreases to the desired ground speed, which is usually the lowest possible speed, position 4, move the cyclic forward to place the helicopter in a proper attitude for landing. In many light helicopters, the student pilot can sit in the pilot's seat while the instructor pulls down on the helicopter's tail until the tail rotor guards or stinger touches the surface. This action gives the student an idea of airframe attitude to avoid, because a pilot should never allow ground contact unless the helicopter is more nose low than attitude. Limiting the flare to that pitch attitude may result in slightly faster touchdown speeds, but will eliminate the possibility of tail rotor impact on level surfaces. So, the landing gear height at the time should be approximately 3 to 15 feet AGL above ground level, depending on the altitude recommended by the manufacturer. As the apparent ground speed and altitude decrease, the helicopter must be returned to a more level attitude for touchdown by applying forward cyclic. Some helicopters can be landed on the heels in a slightly nose-high attitude to help decrease the forward ground speed, whereas others must land skids or landing gear level to equally spread the landing loads to all the landing gear. Extreme caution should be used to avoid an excessive nose-high and tail-low attitude below 10 feet. The helicopter must be close to the landing attitude to keep the tail rotor from contacting the surface. At this point, if a full touchdown landing is to be made, allow the helicopter to descend vertically, position 5. Increase collective pitch as necessary to arrest the descent and cushioning of the landing. The collective application uses some of the potential energy in the rotor system to help slow the descent rate of the helicopter. Additional anti-torque pedal is required to maintain heading as collective pitch is raised due to the reduction in rotor RPM and the resulting reduction effect of the tail rotor. Touchdown in a level flight attitude. Control response with increased pitch angles will be slightly different than normal. With a decrease in main rotor RPM, the anti-torque authority is reduced, requiring larger control inputs to maintain heading and at touchdown. Some helicopters have a canted tail stabilizer like the Schweitzer 300. It is crucial that the student apply the appropriate pedal input at all times during the auto rotation. If not, the tail boom tends to swing to the right, which allows the canted stabilizer to raise the tail. This can result in a severe nose tuck that is quickly corrected with right pedal application. A power recovery can be made during training in lieu of a full touchdown landing. Refer to the section on power recovery for the correct technique. After the helicopter has come to a complete stop after touchdown, lower the collective pitch to the full down position. Do not try to stop the forward ground run with the aft cyclic, as the main rotor blades can strike the tail boom. Rather, by lowering the collective slightly during the ground run, more weight is placed on the undercarriage, slowing the helicopter. One common error is holding the helicopter off the surface versus cushioning the helicopter on the surface during an auto rotation. Holding the helicopter in the air by using all of the rotor RPM potential energy usually causes the helicopter to have a hard landing, which causes the blades flexing down and contacting the tail boom. The rotor RPM should be used to cushion the helicopter on the surface for a controlled smooth landing instead of allowing the helicopter to drop the last few inches. Common errors. Not understanding the importance of an immediate entry in auto rotation upon power plant or driveline failure. Failing to use sufficient anti-torque pedal when power is reduced. Lowering the nose too abruptly when power is reduced, thus placing the helicopter in a dive. Failing to maintain proper rotor RPM during the descent. Applying Up collective pitch has an excessive altitude. At an excessive altitude resulting in a hard landing, loss of heading control, and possible damage to the tail rotor and main rotor blades. Failing to level the helicopter to achieve the manufacturer's preferred landing attitude, failure to maintain ground track in the air and keeping the landing gear aligned with the direction of travel during touchdown and ground contact, failure to minimize or eliminate lateral movement during ground contact, failure to go around if not within limits and specified criteria for safe auto rotation. So we'll hold off there. That is page 2 through 5. That is auto rotation, just a straight in auto rotations. All right, that's chapter 11, Helicopter Flying Handbook. See ya.